So now we begin chapter 7, which contains two sections in our course, section A and section B. And in section A, we talk about the fundamentals of probability. And so probability can get a little tricky, but the best way to understand probability problems is to try to imagine the scenario at hand. So most of the time we are dealing with something that you're doing physically, right? So like, tossing two dice, tossing a coin, selecting a card out of a deck of 52 cards, selecting a marble out of a bag. And so if you try to imagine yourself actually doing this, or if you have a deck of cards, or if you have some dice, or if you have a coin, then that can help you put this into more relatable terms. So we have three main types of probability. We have what's called theoretical probability, relative frequency probability, which is also known as empirical probability. We have subjective probability. Then we have what's called a probability distribution. And then we talk about some various types of probability problems. So this chart right here, this shows you the range of a probability answer, essentially. So the probability of an event expressed as, and so we usually write it as this, capital P for probability, parentheses, and then we put the event. And so the event is what we're saying is we want. So for example, what is the probability of getting a heads when you toss a coin, right? So then this inside would be heads. And then the probability is always between 0 and 1. So if it's 0, that means this is impossible to happen. And if it's 1, it means certain. And in math, when we say certain, that means guaranteed. That means every time you do this, you will get this occurrence. So for example, say you say, what is the probability of getting a number less than 7 when you toss a dice, a 6-sided dice? Well, every single time, right? Because every number on a 6-sided dice is less than 7. And so there you have that 100% or 1 probability. 0 could be something like, what is the possibility or probability of selecting a, red marble in a bag that only has blue marbles? Well, none, right? There's no chance. So that's your 0 or 0%. So here we're going to do a little example. So you can do this on your own, or you can watch me do it. So it says the following game is for 2 players. So I'll just play for both. Each player flips 1 coin. Player A gets 1 point if the coins match, as in both coins land on the heads, or both coins land on the tails. And then player B gets 1 point if the coins do not match. So in other words, if you get like a head and a tail, or a tail and a head. So A says, do the rules of this game seem fair to you? Which player would you rather be? Well, at this point, you may not know, right? It may seem like, well, it probably doesn't matter if I'm A or B. We probably have the same chance of winning. Or maybe it's actually more likely that A wins, or more likely that B wins, right? But at this point, we don't really know. So, our answers may vary in this case. You could say, yes, game seems fair. Or you may say, no, the game doesn't seem fair. Right? At this point, it's speculation. So let's look at actually playing the game. So it says play the game 30 times. Record the results in the table. All right, so let's go. So this is player A. Okay, it landed on heads. And it landed again on heads. So player A gets a point. That's 1 time. All right, repeat. Okay, tails. And this was a heads. So now player B gets a point. All right. Tails, heads. Okay, heads, tails. Okay, tails. And it actually rolled it on a head. It's 5 times. Head. This was a tails. Tails. And tails. So now get a point there. Head, tails, head, tails, head, 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 tails, tails, and tails, head, head, so that was a head, another head, okay, so that was a tails and a head. That was a tails and a head. So 5, 10, 15, 16, 17. All right, we got 13 more tries. Tail and tail. Tail and tail. So these are both heads. These are both heads. So that was a tail, and that was a head. Tail, tail, head. So head, head. Head and tails. Head, head. So head and tails. Tails, tails. 2 more times. Head, head. Tails, and head. So that makes it 30 times. So here we have 16. And here we have 14. So, did the results from playing the game change your mind to question A? Well, I would say yes. Because a fair game should result in each player winning close to half attempts, we could say, which would be 15. Now, you may do it another time, and this may be different, right? You may have 20 and only 10. Then doesn't seem very fair, right? So at this point, playing this game 30 times, it seems like it is more or less fair. And why do we say half? Well, because when you toss a coin, you only have two options. It's either a head or a tail. And so you have a 50% chance of getting either one. Now, relative frequency or relative frequency probability predicts the likelihood of an event based on, and this is very important because this is the difference between relative frequency probability and theoretical probability. So in relative frequency probability, we're basing our probability on the actual observed data. So we actually have to conduct an experiment of the results, as opposed to just doing it theoretically, which means just mathematically knowing that there's a 50% chance every time we toss a coin. So here kind of gives you the way you set up your fraction. So you have the number of times the event actually occurred over the total number of observations. So use the data collected during your game to calculate the relative frequency probability that each player wins. So what was the relative frequency probability that a player A wins, which means either both heads or both tails? Well, let's see. We make our fraction. All right. How many times did this actually occur? Well, if we look back at our table, it occurred 16 times. Out of how many total observations? Well, we played the game 30 times. And there we go. Now, we always leave our probability as a reduced fraction or percent. So both are correct. It's up to you. I usually leave it as a reduced fraction unless it specifically asks for a percent or percentage. But you always, always, always reduce. And so here, 2 would go into both of these. And so if we divide 16 by 2, we get 8. And if we divide 30 by 2, we get 15. And this is reduced because there is no common factor between 8 and 15. So this is our probability. Now, what is the relative frequency probability that player B wins? Well, and that means when they don't match. So when you get like a head or a tail or a head. And here we observed that there were 14 occurrences out of a total of 30. So then again, our final answer is always going to be reduced. So 2 goes again into both. So then this becomes 7 out of 15. And this is our probability. All right, so this is our how to find relative frequency probability. You base it on actual observed data. Okay, and now let's talk about theoretical probability. All right, so the relative frequency probabilities you calculated may or may not support a fair game. However, we can use the idea of theoretical probability to prove whether the above game is truly fair. Theoretical probability predicts the likelihood of an outcome or events based on what we would expect to happen in an ideal world. We calculate theoretical probability as follows. On the top of the fraction goes the number of ways the event can occur, and on the bottom goes the total number of possible equal likely outcomes. So now let's think about the theoretical probability that each player wins for the previous game. When 2 coins are flipped, there are 4 equally likely ways in which the coins can land. Okay, so these are the 4 options. You could either get both heads. You could get the first one being a head and the second one being a tail. You could get the first one being a tail and the second one being a head, or you could get both of them being tails. And that's it. There's no other option of outcome when you toss 2 coins than this. Now, A, calculate the theoretical probability player A wins. In other words, that the coins match. So, remember, on the top goes the ways that the event can occur. So there are 2 ways it can occur, both of them heads or both of them tails. On the bottom, we have the total likely outcomes. So what are all the different possibilities that could happen when you toss 2 coins? These 4. So we end up with 2/4, which again is 1/2. Always simplify your fraction. Or if you want at this point, you could also write that as a percent. So there is a 50% chance that player A wins. Now, calculate the theoretical probability that player B wins. In other words, that they don't match, which means the head and tail or tail and heads. And so here again, right, we have probability. And then here we'll do head, tail, or tail, head equals. Okay, this is always how you set up. Okay, you don't just want to write a fraction with nothing in front of it, because then we don't know what are we trying to find. Okay, so always write this first, the probability, and then write the event you're trying to find in the middle. So there are 2 things that we're looking for, so that goes on the top, and then there were 4 possibilities, so that goes on the bottom. So again, we simplify, we get 1/2. So if we change this into a percent, it's again 50%. So there is a 50% chance that player B wins. In other words, that the coins don't match. Based on the theoretical probabilities, are the rules of this game fair? And then why? So here we have the same chance, theoretically. So yes, this game is fair. We could say, let me use black. The game is fair because each player has the same chance of winning. And if you look back at when we actually did the relative frequency or empirical probability, we got very closely, right? Very close to half. One was 16/30 events, and then the other one was 14/30. So pretty close. Now let's do some practice. A fair 6-sided dice is rolled 1 time. The die can land on either a 1, 2, 3, 4, 5, or 6. What is the probability that the die lands on the number 5? And so we know this is a theoretical probability because it's not telling you to do it. It's not saying, now, toss your dice and record your answer. And so whenever they just straight up ask you what is the probability of something, and they don't tell you to actually gather data, that's always going to be theoretical probability. So again, we start off with, well, what are we looking for? So we're looking for the probability of what? Roll a 5. All right, so let's do our fraction. So when you toss a 6-sided dice, how many different outcomes can occur? Well, 6, right? These are the 6 outcomes that it can occur. Now, how many are the outcomes of the event we're looking for? Well, there's only 1 5 in this 6, so you have your 1. And there you go. Can 1/6 be simplified? No, it cannot. So this is your probability, 1/6. Then again, you can change it to a percent if you would like. What is the probability that a die lands on a number less than 7? Okay, so we can say probability roll number less than 7. All right, well, let's see. You still have 6 options, right? That's not going to change. If you toss a 6-sided dice, there are going to be 6 options. Now, how many of these 6 options are less than 7? Well, every single one, which means here we have 6/6, which can be simplified to 1. So looking back at our chart, 1 means it is certain. This event will always occur. All right, let's look at C. What is the probability that the die lands on a number greater than 7? So here we're looking at the probability of a roll of a number greater than 7. All right, so let's see. Well, we still have 6 possibilities. That's not going to change. Now, how many of these possibilities are greater than 7? That goes on the top. So if you look here, are any of these numbers greater than 7? No, which means 0. Now, what is 0 divided by 6? It is 0. So what does this mean? This means impossible. Okay? Just like if we get a 1, certain. All right, let's continue. So now we look at cards. So the history of probability is actually very interesting because probability became a field of study really in mathematics because people wanted to gamble and they wanted to know, is this game, am I going to win and make money or am I going to lose money? And that's really what started probability and investigations into probability and is a game fair or is it not? So here it shows a diagram of a standard deck of 52 playing cards. Okay, so when you have a deck of cards, you have 4 suits: clubs, spades, hearts, and diamonds. All right, and then in every suit, there are 13 cards. Okay, and so they all have the same type of card. So you have an ace in all the different suits. And then you have 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you have what's called face cards, which are the jack, the queen, and the king. All right, and so clubs and spades, these are black. And hearts and diamonds are red. So put that here, black. And these are red. All right, so here they're saying, what is the probability that a card selected at random is a jack of diamonds? So again, theoretical probability, because we are not actually taking a pack of cards and selecting. We're not actually calculating data or doing an observation. So it has to be theoretical probability. So here we have our fraction. Now, how many cards are there? How many possibilities? There are 52. So that goes on the bottom. Now, how many of these cards are a jack of diamonds? So how many jack of diamonds are there? So here are diamonds, and we go here. And there's only one, right? There's only one card that is a jack of diamonds. And there we go. That is our probability. Now, what is the probability that a card selected at random is red? Okay, so if we wanted to put this, we could say probability. We don't really have space to write it all out, but we could just say something like this, jack of diamonds. All right, what is the probability that a card selected at random is red? Okay, so here, probability of red. So we still have 52 cards. That's not going to change. But how many of them are red? Well, 2 suits are red. And there are 13 in one suit and there are 13 in another suit. So 13 plus 13 means 26. So 26 out of those 52 cards are red. If we simplify this, we get 1/2, which is our answer. Now, what is the probability that the card is a heart? So probability of a heart. So we still have 52 cards total. And how many of these cards are hearts? Well, there are 13 hearts. So that goes on the top. Now we simplify 13 over 52. Well, 13 divides both, so we end up with 1/4, or 25% chance. What is the probability that the card is an ace? So here we have probability of an ace. So we still have our 52. But how many aces are there? 1, 2, 3, 4. So we have 4 over 52. Now if we divide this, we get 1 out of 13. All right, let's look at E. What is the probability that the card is an ace or a king? All right, so probability, ace or king. All right, well, we still got 52 cards. That's not going to change. Now, what are we looking for? What is our event? It's an ace or a king. So how many aces do we have? We have 4 aces. And then how many kings do we have? We have 4 kings. So altogether, we have 8 different outcomes that will give us an ace or a king. So that goes on the top, 8. Now we have to simplify. So if we divide them by 4, we're going to get 2 over 13. And that is our probability. Okay? So remember, even if it doesn't tell you, you always simplify your fraction. Okay? Unless it's just asking you for the percent, then you can just directly divide your original fraction and multiply by 100. But if it's just saying what is the probability, and you're leaving your answer as a fraction, it must be reduced. All right, let's look at another problem. What is the probability that a randomly selected person has a birthday in December? And then here it tells you, note, the month of December has 31 days, and assume there are 365 days in a year. So, probability, all right? And then what are we looking for here? Birthday in December. All right, so remember, the bottom goes to total possibilities. In other words, how many days are in a year? 365. Okay, and then what are we looking out of these 365 days in the year? What specifically are we looking for? We're looking for the month of December, right? Anyone born in December. So we have 31 options for this to happen. And there you go. This fraction cannot be simplified, so we could leave it like this. Or if you want to change it into a percent, it's about 8.45%. About. All right. So when you're just dealing with one event, right? When it says the probability to one thing, like a card, a coin, a dice, a event, it's just one fraction. The bottom is that total possible outcomes, and the top is how many outcomes of the type that we're looking for, of that specific event. Now here is a little information about rounding. It says, if possible, express a probability as an exact fraction or decimal. Otherwise, we typically round the resulting decimal to 3 significant digits. For example, the probability of winning the grand prize in the Super 9's Texas Lotto scratch-off is 79 out of 1,910,287. If we were to write that probability as a decimal, we would get this very large decimal here. Now, it would be incorrect to round this to 0, right? Because what does 0 mean? A 0 means it is impossible to get this occurrence. Well, if it was impossible to win at the lotto, nobody would play it. Right? So we could not round it to 0. Here we would have to round it to what's called significant digits. Okay, and what is a significant digit? A significant digit means it's not 0. So we go to the first one that's not 0, we get 3 of them, and then we round it. And so that's why we would either leave it as this or as this. Okay, so this occurs when we have very small probabilities. Now, comparing relative frequency with theoretical frequency. Now, we would expect that the relative frequency probability of the event occurring to get closer and closer to the theoretical probability of the event occurring as the number of observations gets bigger. This concept is called the law of large numbers. Okay, and so like we saw when we started this section, we only tossed the coins 30 times, and yet we still got a relative frequency probability that was pretty close to what it should be in a perfect world, which is your theoretical probability. But imagine if we did it 100 times or 500 times or 1,000 times or 10,000 times, right? As you get to repeating the experiment to a very large number of times, this is when your relative frequency probability ends up reaching your theoretical probability. And that's how you know it's fair. If it's not, so say you toss it 1,000 times and you don't get a fair probability, so say it's like a 60% chance of doing it with one event occurring and then say a 40% chance of the other, then this is probably an unfair game, or maybe you have a loaded coin or a loaded dice. Now, there are two possible outcomes when flipping a single coin, either a head or a tail. So the probability that the coins land on a heads up is 1 out of 2, or 50%. And the probability that a coin lands a coin lands tails up is 1 out of 2, or 50%. If we only flip a single coin 4 times, would it be too surprising for the coin to land on its heads 3 out of the 4 times? Well, if we're only flipping it 4 times, that is a very small number. So here, the law of large numbers would not apply, and it is possible. I mean, it wouldn't be too surprising because we're only tossing it so few times. So this wouldn't be surprising. All right, let's continue. Now, suppose you toss a coin 200 times, and the coin lands on its head 105 times, which means it landed on its tails 95 times. Do you have reason to suspect that the coins are unfair? No, we don't. We could say, since 200 flips is a relatively large number of times, we would expect the relative frequency probability, which was 105 over 200, to closely model the theoretical probability, which would be 100 out of 200, and 105 is very close to 100. So we have no reason to suspect that the coins are unfair or loaded. Now, suppose you toss a coin 200 times and a coin lands on heads 49 times. Do you have reason to suspect that the coins are unfair? Well, yes, definitely, because how many times then did it land on tails? 151 times, right? That's 3 times more than it landed on its heads. And so we can definitely see an unfairness here. And so we could write yes, right? And then we would say, since 200 flips is a relatively large number of times, we would expect the relative frequency probability which in this case is 49 out of 200, to closely model the theoretical probability, which is 100 out of 200, but it does not. All right, so now we turn to subjective probabilities. So a third method for determining probabilities is to estimate a subjective probability using experience or intuition. For example, you can make a subjective estimate of the probability a friend will be engaged within the next year, or of how happy you will be purchasing a certain model of a car. So 7, assume you are rolling a single fair dice. Identify the method reflected in the following statements as either relative frequency probability, theoretical probability, or subjective probability. So let's see the first one. I am certain that you will roll a 4. Okay, so this is definitely subjective because it's kind of right here, right? Subjective is like an opinion. Maybe you've watched the person many times and they just always roll a 4 or very often. So you may make this statement, right? But this is not based upon any actually like an actual observation, and it's not based on that ideal scenario of theoretical. So this would just be subjective. Now, after 20 rolls, the die landed on the number 4 a total of 5 times. According to this data, the blank probability of rolling a 4 is 5 out of 20, or 1/4. Okay, so here, this is very key information to tell you that it is relative frequency, because it's telling you after 20 rolls. Okay, it's telling you exactly what happened. The die landed on 4 5 times, and then it didn't land on it the other 15 times. So this is not ideal. This is not in the perfect scenario. This is something that actually happened. So this is relative frequency. The blank probability of rolling a 4 is 1 out of 6 because there are 6 possible numbers on which a dice can land, and there's only one number of 4. See, this is theoretical probability because it's stating the simple fact, right? That there are 6 possibilities and there's only one 4. So this is the theoretical probability. We're not actually conducting an experiment. Now we talk about what's called the probability of an event not occurring. Okay, so often the possible outcomes for a given experiment can be split into 2 groups. So not always, but often. Either a certain event occurs or the event does not occur. Okay, and these kind of probabilities happen when you have an event that can only be one or the other. So for example, with a coin, you can have a head or a tail. You cannot have both a head and a tail. And so that kind of a problem would give us this type of probability where we could figure out what is the probability of not rolling a head or of not rolling the tails, etc. So it says, consider rolling a single fair 6-sided dice. What is the probability that you roll a 3? Okay, so here, theoretical probability, because it's not telling you to actually do it a certain number of times. It's just asking you, what would be the probability of rolling a 3 if you have a 6-sided fair dice? Well, there are 6 options, so that goes on the bottom. And then how many 3s are there in those 6 options? Well, there's only one. So there you go. The probability of rolling a 3 is 1/6. What is the probability that you don't roll a 3? Okay, so again, we still have 6 options, but think about it. How many of these 6 options are not a 3? Well, we have 1, 2, 4, 5, and 6. So that is 5 options. So our probability of not rolling a 3 is 5 out of 6. Now add the probabilities that we found in these previous parts. So if we add 1 over 6 plus 5 over 6, what do we get? We get 6 over 6, which equals 1. And remember, what does 1 mean in probability? It means that this is a guaranteed or certain event. That means every time you roll a 6-sided dice, you're either going to roll a 3 or you're not going to roll a 3. That's always going to be true. Which pretty much answers D. Why do the probabilities of parts A and B add up to 1? So we can say because one of the two events is certain or guaranteed to happen, you either roll a 3 or you don't roll a 3. There's no other possibility. All right, let us continue. So here, this actually summarizes one way that we can calculate the probability that an event does not occur is we can simply just subtract that event, the probability of that event, from 1. Why? Because we know that both of the numbers add up to 1. So it's like 2 plus 3 equals 5, right? And so then if we did 5 minus 3, we would get 2. And if we get 5 minus 2, we would get 3. So anytime we have a not occurrence, we can simply just subtract the probability that it does occur from 1. So practice. If today's forecast predicts that 0.37 chance of rain, what is the probability that it will not rain today? Okay, and so here our probability is looking for no rain. All right, so we're going to have 1 minus, and then the probability of what? That we do have rain. What was the probability that we're going to have rain? 0.37. So you're going to have 1 minus 0.37, and that is going to give you 0.63. And there you go. This is your probability of it not raining today. And then here's an additional question. Is this a relative probability, like a relative frequency probability, theoretical, or is it subjective? Well, this is a relative frequency probability because there is a prediction of the chance of rain that is happening. So they're predicting it based on the forecast that was observed, right? Moisture in the air, blah, blah, blah. And so this is not something that happens in the ideal world, but this is something that they're specifically predicting for today. So this gives us the idea it is a relative frequency probability. Now, referring to a standard deck of 52 playing cards that we talked about on page 3, what is the probability that a single card selected at random from the deck is not an ace? All right, so here we're doing probability, not ace. So using our little formula above, that means 1 minus the probability of having an ace. So, what was the probability of having an ace? Well, we know we have 52 cards. And then how many aces are in those 52 cards? Well, there's only 4 aces. Now, if we subtract, we need a common denominator. So we can make 1 become 52 over 52. And then we can now subtract. So 52 minus 4 is 48. Over 52. Okay, which can be simplified by dividing by 4, and we get 12 over 13. And there we go. This is the probability, which is very high, which makes sense, right? Because there are so many more cards that are not aces that if you were just blindly pull out a card from a stack, it's very likely that you will not get an ace. So, is this relative frequency theoretical or subjective? Well, did we do any kind of observation or experiment? No. We used theoretical probability, the total possibilities that could happen, which are 52 different cards, and then the 4 cards that we were looking for. So this is theoretical. All right. 11. Based on her performance during a recent season, a player has an 80% chance of making a free throw. What is the probability that the player will miss a free throw? And so here we're looking for probability of a miss. Okay? So what's that going to be? That's going to be 1 minus the probability that she makes it. So we can just say make. Okay? So what is the probability that she makes a free throw? 80%, which is 0.80. So we do 1 minus 0.80, and that gives us 0.20 or 20%. Now, what type of probability is this? Well, here it said what? Based on her performance. Okay, this means it is a relative frequency probability because it is based on observing her playing. All right, now we move on to probability distributions. All right, so a probability distribution lists the probability of all possible events or of a set of outcomes. Follow parts A through C to create a probability distribution for the number of girls in a family with 3 children. Note, for this problem, assume that the gender is either girl or boy. So, first of all, list all gender combinations for a family of 3 children. Be systematic. Okay, so when we are making a list of all possible outcomes, we want to be systematic, and one of the ways we do that is we do what's called a tree diagram. So we start off with the mother, right? Okay, so let's just make a little stick figure here. All right, this is mom. All right, so when mom has a first child, what are her options? She has only 2 options in this case, right? So this would be first child. She could have a boy or a girl. All right, now what about the second child? Well, if she had a boy first, is it possible that she could again have a boy and a girl, or a girl? Yes. So here would be boy, here would be girl, and this would be second child. Okay? And then the same way, if she first had a girl, then again she had a second child. Could again be a boy, or it could be another girl. Now for the third time, she could have a boy, and another boy. Or she could have a boy, and a girl. And this is like the third child. All right, the same thing here. Boy or girl. Same thing here. Boy or girl. And then the same thing here. Boy or girl. So this, by using a tree diagram, it is a very nice, easy, visual, systematic way of making sure that you've accounted for all possible outcomes. So let's see. The first possibility is having 3 boys, a boy, and a boy. Okay, so we're going to say B, B, B. The second way, we could have a boy, and then a girl. So boy, girl. All right. We could have a boy, girl, boy. So boy, girl, boy. We could have a boy, girl, girl. Boy, girl, girl. We could start off with a girl and then have a boy and then another boy. So girl, boy, boy. We could have a girl, boy, girl. girl, boy, girl. We could have 2 girls and then a boy. Girl, girl, boy. Or we could have 3 girls. All right, so this is the total possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 different gender combinations for a family of 3 children when we assume that the gender is either girl or boy. All right. Now, we can use the multiplication principle to verify the total number of gender combination for a family of 3 that we just found in part A. So we have the multiplication principle pretty much tells us that to find the total combinations, we just multiply each individual possibility. So the total number of gender combinations in a 3-child family, so that's where there are 3 spaces for the 3 children. So if we look at the first children, what are the number of gender outcomes? Well, we said 2, right? Girl or boy. When they have the second child, it's the same thing, girl or boy. And then when they have the third child, it's the same thing, girl or boy. All right, and so at this point, to find the total possible combinations, we just multiply. So 2 times 2 is 4, and 4 times 2 is 8. So there are a total of 8 possible gender outcomes for a 3-child family. So as you can see, this is obviously way quicker on finding out the total number of possibilities than actually creating the tree diagram. However, the tree diagram can really help you understand what's happening as well as answer some probability questions that they may ask you. So part C says, suppose we are interested in sorting the total number of gender combinations for a 3-child family based on the number of girls in each combination. There are 4 possible events based on the number of girls in a 3-child family. Okay, so here we're only talking about the girls, right? And so a family can either have 3 girls out of 3 children, 2 girls out of 3 children, 1 girl out of 3 children, or no girls out of 3 children. Okay, so use the equal likely combinations listed in part A to create a probability distribution for the number of girls in a family with 3 children, as shown in the table. Okay, and this is what we call a probability distribution, when we list the possible events for a certain event. So, probability of girls. Right, and we have here the different options. So here's 3 girls. So that's what it says, probability 3G. All right, so if we look back here, right, how many possibilities do we have of having 3 girls? Only 1, right? This is the only occurrence where we have 3 girls. So our probability, right, we have the total outcomes, which is 8. And how many of those 8 outcomes do you get 3 girls? Only 1. Now, what is the probability of getting 2 girls? So let's look back here. Okay, so let's see. Do we have 2 girls here? No. 2 girls? No. 2 girls? No. 2 girls? Yes. So we got 2 girls here. 2 girls? No. 2 girls? Yes. 2 girls? Yes. And there we go. So we have 3 possibilities of having 2 girls. We could have a boy and then 2 girls. We could have a girl, a boy, and a girl, or we could have 2 girls first and then a boy. So when we do our probability, it's still 8 total outcomes, but we have 3 of them can be girls. And these neither can be simplified, so that is our probability. What is the probability of having only 1 girl? So let's look at that now. So probability of only having 1 girl. Well, there's no 1 girl here. Here there is 1 girl, so check. Here is another just 1 girl, so that's a check. Here is 1 girl, so that's a check. And then that's it. So again, here we have 3 possibilities of only having 1 girl. So going back to our probability distribution, we now have 8 total on the bottom and 3 again on the top. Now, what is the probability of having no girls? So if we look at our 8 possible outcomes, how many of these have 0 girls? Well, this has girls, this has girls, this has girls, this has girls. All of these have girls except this one, where you have the 3 boys. So we have 1 out of the 8 options where we have no girls. So 8 on the bottom, 1 on the top. All right, and for a total, if we add these up together, we're going to have 1 plus 3, which is 4, 4 plus 3, which is 7, and 7 plus 1, which is 8. So we get a total of 8 over 8, which equals 1. So when you make a probability distribution, your total probability should always be 1, because these are taken into account all the possible events. And so if we add up all the probabilities of possible events, we should get 1. We should get that it is certain to happen. All right, let's look at another example of a probability distribution. So here we are talking about dice. So the diagram below on the left shows all the ways which a pair of dice can land, written as an ordered pair in the form. So this is what we call an ordered pair. So the first number is the result of the first die, and the second number is the result of the second die. There are 36 possible equally likely outcomes. Suppose we are interested in the sum of the dice. We can display the probability of every possible event, which is the probability of every possible sum, in a table called a probability distribution. Okay? So, here we have it. Why is there 36? Because remember, using the multiplication principle, we're only doing 2 dice, so there are 2 things being multiplied. How many options do we have here? 6. How many options do we have here? 6. So 6 times 6 gives you 36. So our probability distribution here, we have a sum of 2, right? It is impossible to get a sum of 1 or 0. The smallest sum you can get is 2 when you're rolling 2 dice. So how many times do we get the 2? Only 1 time. So what is our probability? Well, 1 out of how many events? 36. If we change that into a decimal, we get approximately this amount. Now, let's go to 4. So, how many ways do we have 4? So, 1, 2, 3. All right, so then here we're going to have 3 out of 36, which, if we simplify to 1, 12. Then again, if you want to round this, you can. I really don't require it. Because a exact fraction is acceptable, it's even preferred, but you can also kind of approximate it to a decimal if you want to. Okay, I'm not going to do that for everyone, but if you want to, you could. Now let's see a sum of 5. So they started off for us. So here we have 1 plus 4, that gives us 5. This is 2 plus 3, that gives us 5. 3 plus 2. Gives us 5, and then 4 plus 1 also gives us 5. And that's it, because if we go to the next one, we're already at 6. So how many ways do we have to get 5? 1, 2, 3, 4. So the frequency would be 4. So now we would have 4 out of 36, which simplifies to 1 over 9. All right, let's see sum of 6. So 1 plus 5 is 6. 2 plus 4 is 6. 3 plus 3 is 6. 4 plus 2 is 6. And 5 plus 1 is 6. And then we go to the next one and we're already at 7. So how many times did this occur? 1, 2, 3, 4, 5. So we have a frequency of 5, which means 5 over 36, which cannot be simplified. All right, moving on to 7. So 1 plus 6 is 7. 2 plus 5 is 7. 3 plus 3 is 7, 4 plus 3 is 7, 5 plus 2 is 7, and then 6 plus 1 is 7. So how many occurrences do we have? 1, 2, 3, 4, 5, 6. So there's a frequency of 6. So our probability will be 6 out of 36, or 1/6, as it simplifies. All right, sum of 8. So let's see. We have a 2 plus 6, which is 8. A 3 plus 5, which is 8, a 4 plus 4, which is 8, a 5 plus 3, which is 8, and a 6 plus 2, which is 8. So we have 1, 2, 3, 4, 5, a frequency of 5, and a probability of 5 over 36, which cannot be simplified. Now let's see 9. We have 3 plus 6, which is 9. We have 4 plus 5, which is 9. We have 5 plus 4, which gives us 9. And we have 6 plus 3, which gives us 9. So what is our frequency here? 1, 2, 3, 4. So our probability is 4 out of 36, which can be simplified to 1/4. 9th. All right, a sum of 10. So if we do 4 plus 6, we get 10. 5 plus 5 gives us 10. And then 6 plus 4 also gives us 10. So the frequency is 3 times. So 3 out of 36, which can be simplified to 1/12. All right, sum of 11. There's only 2 ways you can get 11, by rolling 2 die. And that is 5 plus 6, which is 11, or 6 plus 5, which is 11. So we have 2, or 2 out of 36, which simplifies to 1 out of 18. All right, and last one, the way to make a 12. Well, there's only one way, and that's 6 plus 6. So probability is 1 out of 36. Now, if we were to add up all these probabilities, we should get exactly 1. Okay, every single time you make a probability distribution, your total probability should add up to be 1. Now, B says, notice that the sum of the probabilities listed in the probability distribution add up to 1. Why? Well, we could say when we roll 2 dice, we are certain or guaranteed to get a sum between 2 and 12. And then we can say inclusive, which means including the 2 and the 12. Okay, we're guaranteed every single time this is going to happen. So we have a probability of 1 or 100%. All right, moving on. So, the table to the right shows the gender and political party of the 100 delegates at a political convention. Suppose you encounter a delegate at random. Okay, so you randomly encounter a delegate. What is the probability that you meet a man? All right, so here we're going to have probability man. Okay. All right, so what is going to go on the top? So the top should be total men, right? And on the bottom would be total delegates. So, how many men? So, if we look over here, we want to add these up. You get 20 plus 28 is 48. So there are 48 men out of a total of 100 delegates. Okay, so if we simplify this, this should give us 12 over 25. So this is our probability. Or if you want to change it to a percent, it would be 48%. So you have a 48% chance of running into a man at this convention. Now, what is the probability you meet a Republican? So here we have probability of a Republican. I'm just going to abbreviate it. So, what should go on the top? Total Republicans, because that's what you're trying to find out. And on the bottom is still going to be the total delegates. Right? Your total outcomes. The total people you have to randomly meet. So that's still 100. Okay? Now, how many Republicans are there? Where there are 21 women Republicans and 28 male Republicans. So if we add 21 plus 28, we get 49. Which cannot be simplified. So we could leave it as a fraction. Or 49% if we want a percentage. What is the probability that you meet a male Republican? Okay, so here we're looking for two things. Be male and Republican. Okay, so you still have the total delegates down here. That's not going to change. But then this is going to be male Republican. Okay, so let's see. This is still 100. There are 100 delegates. Now, how many of these Republicans are men? 28. Okay, so you can have 28 on the top. Now, this can be simplified by dividing by 4. So this will give us 7 over 25, and that is our probability. Or if you want a percent, this would give you 28%. All right, last question. What is the probability that you meet someone who is not a Republican? So remember, when it has that not word, we can use the 1 minus the probability that it does happen. So we have 1 minus, and then here we already found out the probability of having a Republican from B. So that is going to be 49 out of 100. So again, in order for us to subtract, we need a common denominator. So I'm going to make 1 100 over 100 minus 49 over 100. And then that gives us 51 over 100, which cannot be simplified. So that would be our answer. Or if we want it to be a percent, it would be 51%. All right, so now we practice a bit more of that multiplication principle. So the multiplication principle states if there are m possible outcomes for one process and n possible outcomes for a second process, then the total number of possible outcomes for the two processes combined is m times n. And this applies if there are 3 or 4 or 5 or 10 different events. We just find out the possible outcomes for each event, and then we multiply them. So, a restaurant menu offers 2 choices of an appetizer, 5 choices for a main course, and 3 choices for a dessert. How many different 3-course, so appetizer, main course, dessert, meals are possible? So, let's look for our options. So we have 2 choices here, we have 5 choices here, and we have 3 choices here. So the multiplication principle tells us all we have to do is multiply. So 2 times 5 times 3. 2 times 5 is 10, and 10 times 3 is 30. So there are 30 different 3-course meals. Very, very simple. All right, a college offers 12 natural science classes, 15 social science classes, 10 English classes, and 8 fine arts classes. You must take 1 class from each category to meet your core requirements. How many possible ways are there to meet the core requirements? So again, this is a multiplication principle. So we're going to just multiply. So 12 times 15 times 10 times 8. Okay, you multiply these together and you get 14,400 different ways to select your classes. All right, now this one is pretty interesting. This is why there are so many different possibilities for vehicles and why nobody has the same vehicle plate number as anybody else. So how many license plates are possible for a plate that has 7 entries, where the first 3 entries are letters and the remaining 4 entries are digits? Okay, so again, possible plates. So this is the multiplication principle. So what I do is I like to, especially in this case, we have 7 different options. So 1, 2, 3, 4, 5, 6, 7. Now, the first 3 are supposed to be what? Letters. And then the 4 here are supposed to be what? Numbers. So remember, it's the first one says assume letters and numbers can be repeated. For example, this could be AAA or BBB or CCC, etc. So let's look at the total possibilities of each individual one, right? Then we multiply them all. So if we look at the first choice, right? How many letters do we have? Well, we have 26 different letters that we could put in the first place of the license. So we've got 26. Now, because we can repeat, there are again 26 options here. And again, 26 options here. Now, what about numbers? Well, you can only put single digits, so it could be from 0 to 9. That is 10 different options. And again, they can repeat. For example, this could be, 9999 or 1111. So here you have 10 options. You have again 10 options here. You have again 10 options here, and again you have 10 options here. So if we multiply these 7 numbers together, it's going to give us, so I'm going to write there are, and now we're going to write it, so it's going to be 175,760,000 possible license plates. So that's a lot, right? 175,760,000 different possibilities. Now let's see if the outcome changes when we assume that letters and numbers cannot be repeated. So just thinking, intuitively, if it cannot be repeated, you should have a fewer number of possibilities. So again, we're going to have the same thing. We have 7 digits. 4, 5, 6, 7. Okay, and again, the first 3 are letters. And then the 4 are numbers. Now, when we select our first letter, we have 26 options because nothing's been used. However, when we have the second, so let's say we picked a J. Okay, now can these be J's? No. So when I go to pick my second letter, I cannot select J, which means I don't have 26 options anymore. I only have 25 options. And when I get to pick my third letter, so say I pick here B, I can no longer select a J and I can no longer select a B, which means now I only have 24 options for the third letter here. Now, when I go to my numbers, when I start off with my first number, I have 10 options, 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. But if I select a number, so say this is an 8 now, when I select my second number, I can no longer select an 8, which means I only have 9 options. And then when I select my third number, I'll only have 8 options. And when I select my fourth number, I will only have 7 options. And now when we multiply these, we'll say there are, if you multiply these numbers, you're going to get 78,624,000 possible license plates. Okay, so that's how you do it when it can be repeated and when it cannot be repeated. All right, on to the last page. So in this last page, we talk about odds. And so we don't have a huge focus in this course on odds, but we do have, a brief introduction, because odds is probably something everyone has heard about, and that is pretty much anytime you gamble or make a bet, they tell you the odds, right? So what does it mean? Odds for an event, odds against an event. So another common term for probability is odds, but strictly speaking, the two terms have different meanings, okay? So if you say the probability is 25%, the odds is not going to be the same as 25%, okay? Even though sometimes when people speak, they use probability and odds interchangeably, they're actually two different values, okay? The probability and the odds are almost never the same. Now, odds are commonly stated as a ratio of the probability that an event will occur to the probability that it will not occur. Note that in gambling, the term odds on generally means odds against. Okay, so when they use what are the odds on, it means odds against. And these are our two formulas. So to find the odds for an event A, we take the probability of event A and we divide it by the probability of not getting event A. And then we have odds against the event. It really is the reciprocal, the reverse. So on the numerator, we have the probability of not getting A divided by the probability of getting A. So probability versus odds. So suppose you roll a 20-sided dice, okay? So there are 20 different numbers from 1 to 20. Find the probability that you land on an even number, okay? So here we are looking for an even number. So first, let's figure out, if we have a 20-sided dice, how many even numbers are there? So the smallest even number is 2. Then we would have 4, 6, 8, 10, 12, 14, 16, 18, and 20, because it's a 20-sided die, so it will have 20. Now, will it have 22? No. So that's it. These are all the even numbers. Now, the probability of even. So remember, to find the probability, we take the total possibilities. So if it's a 20-sided dice, there are 20 different possibilities. And then how many are even? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So simplify gives us 1/2. Our probability is 1/2 or 50%. Now, what are the odds for landing on an even event? So here we're looking at odds for, we can say even number. All right, so on the top, we're going to have what? Probability of it being even. And on the bottom, probability of not even. Well, what is not even? Odd. So we already found out the probability of it being even is 1/2. Now, the probability of it being odd would also be 1/2, right? Because every other number is odd. Now, if we simplify, right, when you have a fraction divided by a fraction, if the denominators are the same, they actually cancel. So this is the same as 1/1. Okay? So our odds are going to be 1 to 1. Okay? We like to write it as a ratio, which is where we use those two dots. Okay, so you see the probability and the odds are not the same thing. Because to find the odds, we're actually dividing two different probabilities. All right, look at C. The probability that you land on a number divisible by 3. So here's just probability. So how many numbers divisible by 3 are in this 20-sided dice? Well, the first number would be 3. Then 6 is another number, 9, 12, 15, 18. And then the next number would be 21, but 21 would not be on a 20-sided die, so that's it. So, probability. And then we could say number divisible by 3. All right, so the probability is going to be what? Well, we have 20 total outcomes. That's not going to change. And then here we have 1, 2, 3, 4, 5, 6. So there are 6 outcomes where we have a number divisible by 3. Now we can simplify this by 2. So 6 divided by 2 is 3, and 20 divided by 2 is 10. And there we go. This is our probability. Now, what are the odds against landing on a number divisible by 3? Okay, so here we have odds against or on a number divisible by 3. So when it's against, we have the probability of not. I'm just going to put divided by 3 to make it easier. And then on the bottom will be the probability, and then yes, divide 3. So here we had 6 out of the 20 that were divisible by 3, which means 14 out of the 20 are not divisible by 3. How many were divisible by 3? 6 out of 20. So again, to simplify, this is called a complex fraction when you have the denominators the same, that you just cancel the denominators. So it's just going to be 14 divided by 6. This can be simplified by 2, so 14 divided by 2 is 7, and 6 divided by 2 is 3. Okay, so how do we write this? 7 to 3. These are the odds against. All right, last thing, application of odds. So these are word problems where we apply what we learned about odds. So when a bookmaker offers betting odds of A to B, that's how you read this, against some event occurring, it means that he or she is prepared to pay out a prize of A dollars for every B dollars at stake, and return the stake to anyone who makes the stake that the event will occur. So number 1, at a horse race, the odds on Blue Moon are given as 7 to 2. Okay. So in this problem, the 7 is like your A, and the 2 is like your B. Okay. If you bet $10 and Blue Moon wins, how much money will you gain? Okay, so let's see. We have 7 to 2. Okay, so we could read this as $7 for every $2 you bet. Okay, well, how much did you bet? Okay, so we're now going to have blank earned for blank bet, right? Which is what they want to know. So how much did you bet? You bet $10. So how do you go from a 2 to a 10? You have to multiply by 5, which means we have to multiply this by 5 as well, which gives you $35. So you earn or win $35. Okay. Because remember, odds on is the same thing as odds against. All right, last example. You bet $100 that War Admiral would win a horse race where the odds against him winning are 3 to 2. If he wins, what will you take home? So again, let's do the same thing. So here you have 3 to 2. What does this mean? That means $3 for every $2 that you bet. Okay? So then again, we're going to have blank earned or won for what your bet is. Okay? So what was our bet? $100. So how many bets of 2 are going to give you $100? 50. So we have to multiply this by 50. Okay? And so here you end up with $150. Okay? But this is where it's a little bit different from 1. See, 1 was just asking us how much money did you win, right? How much did you gain? So here you gained $35. Likely here you won $150, right? But what will you take home? Well, you will take home what you won along with the money you placed as a bet. Okay? Because otherwise, imagine this. You placed $100 and then you only got back $150. Well, did you really win $150? No, because then 100 was already yours that you put on the bet. So you win back the amount of money that you bet along with this money. Okay? So take home will be bet plus money won. So the bet was $100. Money won was $150. So the take home will be $250.